So let's first start by using to try to find the radius, because that's one of the most important things that we need to start before we try this problem out. So we need to first find whatever the radius is, and let's call the radius r. So r, this will be r. This segment over here from O, let's call this intersection point. Let's call this intersection point T, and let's call this intersection point R. So we know that OR is R. TO is also basically has a line segment, the line segment also has the length R, as well as OB clearly has a line segment of length R. So to find the radius, let's first apply something called the power of a point between this line. So power of a point between QT and QB. So what this situation would look like is that over here you have QT and over here you have QB. And for power of a point, what it says is that Q times, let's just call this XY. Over here, QX times QT would equal to QY times QB for any of these lines that look in some configuration like this. So like QX times QT is equal to QY times QB, which is the whole thing. Applying that to this situation, let's call this A. We would get that A times, so QR times the whole line segment QT, A plus 2R, this is 2R, this is the radius of the circle, is equal to QC, which is 0.5 times this whole line segment all the way to the line's intersection with the circle, which is QB, and QB is 4.5. Another thing we notice that we can actually get from A and R is that over here we have a Pythagorean relationship. So this is called, so this is 1. The second thing you need to observe is that there's a Pythagorean relationship for QOB. And for this one, you would get you would realize that OR is also radius, so it has length R. So basically over here we get OQ squared plus OB squared is equal to QB squared, and this would just be OQ squared. And from that, what we get is that OQ is A plus R squared, OB is R squared, it's just this line segment, and QB, as we know, is 4.5 squared. So this is our first equation, this is our second equation. It's nice. Well, we have two equations, two variables, A, R, and these are our two equations. Let's just combine them together. So if we have 1 and 2, let's simplify each of the equations first. We get A squared plus 2AR is equal to 4.5 plus times 0.5. So 4.5 is 9 halves, and 0.5 is about a half. So we get 9 halves times a half. And then we get over here, well, let's just keep it as 4.5 times 0.5 for simplicity, actually. 4.5 times 0.5. The second equation, let's expand this out. A squared plus 2AR plus R squared is equal to 4.5 times 4.5. And notice over here that these two terms are common between both of these. So we can simply just subtract these. And what we'll get is 2 minus 1. We will get R squared is equal to, if you subtract these two, first of all, on the left side, if you subtract 2 and 1, the left side you get A squared plus 2AR plus R squared, and you can subtract A squared plus 2AR, and you just got R squared. Over here on the right side, you get 4.5 squared, and then on the right side for equation 1, you get 4.5 times 0.5. So subtracting this, we get 4.5 times 4.5 minus 4.5 times 0.5, which is equal to 4.5 times 4.5 minus 0.5. That is because I factored the 4.5, and we get 4.5 times 4. What is that? That is 18. And notice that this is 2R squared, because there are 2 R's over here. And thus, we get that we get r squared is equal to 9 and r is equal to 3. It cannot be negative since it's a radius, so r is simply just 3. And now we figured out what our radius is. Now let's proceed on and we can go to our to our next step, which is trying to find what BP is, which is the goal of this problem. So to find BP, we need to make another observation. This one will also involve, coincidentally, power of a point and the Pythagorean theorem. So for this one, you need to notice you need to make the observation that over here, to find PB, which is x, we have this triangle. So to find PB, this is step 2. We need to find 1. We need to find the Pythagorean relationship between POB. And for 2, you need to find the power of a point relationship between TR, which is this whole segment, and intersection with AB. Because TR and AB, they all involve x. Or TR and AB, this involves x, and the Pythagorean relationship of POB also involves x. And since we have 2 variables, and later we'll find we only have 2 unknowns, we will be able to solve this problem quite easily. So let's just start, before we even do this, let's start labeling the diagram and making it more clear so that we know what we're trying to solve for. Since this is x, we'll just label some knowns. AB is 5, so AP must be 5 minus x. We also know, we also don't know what the value of TP is, so let's just call this some random name. Let's call this B. All right. And since this is B, and we know that TR is a diameter of the circle because it goes through the point O, and it's perpendicular to this radius, so it has to be a diameter, and it goes through the center. So since this is a diameter and it goes to the center, we know that PR plus TP must be 6, and thus PR must be 6 minus B. And I won't really mention this over here, but you know, I'll just write it down. 6 minus B. So over here, now that we know these values, we also need to find out what this value is. PO. PO is in this triangle that we're trying to solve for, and since we know that PO is a radius, O is the center, T is a point on the circle, then we know that PO has 3 minus B, and this is basically just 3 minus B. So over here, let's solve for our triangle POB first. All right, POB has a Pythagorean relationship, so POB Pythag, we get 3 minus b squared plus r squared is equal to x squared. And we're trying to solve for x, of course. And let's do the power of a point for TR and AB. So so first let's see what the Pythagorean relationship would be, or the power of a point relationship would be for TR and AB. In this case, TR and AB is a different case. Initially, we talked about power of a point where you have 2 lines that intersect outside of the circle, that come to an intersection outside of the circle. But here we're in a different kind of situation. We have 2 lines that are intersecting inside of the circle. And since they're inside of the circle, we have a case that's kind of like this, right? So TR is over here, TR would be over here, and we would get something like this, TR. AB is over here, so we would get something like this. And if we want to try to find the relationship, we would call, let's say this intersection point, we would call, over here is P. What we would get is we would get AP times PB is equal to TP times PR by power of a point for an intersection inside of a circle. So this segment times this segment is equal to this segment times this segment. So having made that clear, let's try to see how that applies to our situation over here. TP over here is length B. We define that because we don't really, we just have an unknown. We don't know what this really is. And this was 3 minus B as we've seen before. This whole thing was a radius. So TP times PR. PR is over here, PR, you can see this 6 minus B is equal to, you know, AB is composed of AP and PB, and over here you have 5 minus X as AP times PB, and PB over here is X. So this will be our power of a point relationship for this for AB and TR, and this will be our Pythagorean relationship for our triangle POB. So again, as you can see over here, same thing just as last time. We have two unknowns. Actually, R over here is 3, so this actually will just be 3. We already know what R is, so R is equal to 3. So again, we have two unknowns, B and X. We have another two unknowns, two equations. Sweet, we have an equation that we can solve. So solving this, let's call this 1 and let's call this 2 just as usual. So for equation 1, let's factor it out. We get 9 minus 6b plus b squared, a squared minus 2ab plus b squared, plus 9 is equal to x squared. That's our equation 1. Second, 6b minus b squared is equal to 5x minus x squared. That's our second equation. All right, so for over here, you'll have to make an interesting observation over here, all right? So at this point, it seems like you have some quadratics and you might have to do some quadratic formula stuff. No, that's incorrect. You don't even need to do all of that, any of that stuff, because if you actually look over here, realize this is negative, positive, positive, negative. And if you add these up, this whole term goes away. And you're just left with 9 plus 9 over here, and over here you're just left with 0. On the right side, you have x squared on this side, positive x squared. On this side, you have negative x squared, and if you add these up, the x squared just goes away, and you're just left with 5x. And just to remind you, what we're trying to find is x, which x is basically our length of our line segment, BP. So over here, with that in mind, let's simplify this. We got b squared minus 6b plus 18 is equal to x squared. These positives are not necessary. Those were just for informational purposes a few seconds ago. For the second equation, we get 6b negative b squared plus 6b is equal to negative x squared plus 5x. So over here, all you would really need to do over here is you just need to add these two equations up. B squared minus b squared is 0. 6b plus 6, negative 6b plus 6b 0 plus 18 is equal to positive x squared minus x squared is obviously 0. And over here we got 5x. And over here, now all we have is we have 18 is equal to 5x. And from this, we simply just divide by 5 over both sides, and voila, you got your equation, or you got your solution. X is equal to 18 over 5. So see how simple this problem was, just by trying to break it down into these pieces. First starting to look at what the radius is. We found out the radius was 3, and then trying to find some relationship between these Pythagorean triangles as well as the power of a point. So with the knowledge of the power of a point and the Pythagorean theorem, this problem becomes quite simple, and it just becomes merely just a two-step process. And as you can see over here, this is not going to be our final answer. You don't put this into your box, because what it wants you is you want to find m plus n. Over here, BP is equal to 18 over 5, and this is simplified terms for m plus n. And since 18 and 5 are relatively prime positive integers, whatever the heck that means, that basically just means that these two numbers do not have a common factor with each other. And these indeed do not have a common factor with each other, so that's our answer that we're just going to give to the AIME is 23. Awesome.